In the last lecture, I had introduced an algorithm called Grover's search algorithm, and we said that this is basically searching a particular item out of an unstructured database of capital N number of items. And our way of doing this was that we define a needle in the haystack function, which has this property that excepting for the item that we are looking for, the function can take in other arguments and it evaluates to 0. But for the particular item that we are interested in, which I will be frequently referring to as the marked item, the function evaluates to 1. The importance of the algorithm lies in the fact that we had seen that classically such a search requires of the order of n. In fact, typically a probabilistic algorithm would require n by 2 searches if you are looking for one item out of n items. Now, so the oracle that we define is like this, that W is our string that I have been searching, n qubit string, and this evaluates to 0 if the input string x doesn't match with the string that I am looking for, and it evaluates to 1 in the case where x is equal to W. This is our normal representation of an oracle. So here we have got the input x, as we have seen several times, that this input is a linear combination of a large number of states, and this y is usually set a value depending upon what you are looking for, and the black box or the oracle, it calculates this function corresponding to this linear combination of the input, and the first line is still input without any change, but the target bit, which was y, becomes y plus the function that you have calculated, so that if y is the null string, then you simply get f of W, and if y is 1, then you get the complement of that. So basically, the idea in this case was to set the target bit y equal to 0 minus 1 by root 2. So therefore, the target bit has 2 components, one 0 and one 1, and 0 obviously will not change the value of the function that you calculate, which is output, but 1 will give you its complement, and it is succinctly written like this, that the output is written as minus 1 to the power this function that you calculate, which if the function evaluates to 0, then it's minus 1 to the power 0, which is equal to 1, and of course x is the input which is left alone, and the target bit is 0 minus 1 by root 2. So this is the phase that is associated with x. You notice that this tells us that the second line or register is unaltered, but the first register has a phase depending upon the value of Fw of x. So this is what we talked about last time, and we will today try to see how this is going to be actually implemented. Last time we also defined a couple of operators. So first one was an operator which we called as the UW, and UW is identity minus 2 times get W bra W. Now notice what happens, that if such an operator acts on the state W, which is the marked state, you get W minus 2W, which is equal to minus W. That is, it simply flips the sign of the marked state. A second operator, which is US, is 2SS minus I. Notice the sense is essentially reversed. So what happens is this, that now S, as I told you, is a uniform linear combination of the computational basis. So n qubit computational basis 1 over square root of n sum over x equal to 0 to n minus 1 of x. Now if this US acts on this S, notice this is a typical structure, S is an operator, so that I get S itself. In other words, if I have an arbitrary vector and I resolve it into a component parallel to S, and a component perpendicular to the S, then the component of this arbitrary vector which is parallel to S will remain unchanged, but the component which is perpendicular to S will change. And we had seen a geometrical interpretation of this, which I will not repeat, and basically what we said is this, that initially, since I start with equal linear combination of the basis state, I start with a W whose strength in the linear combination, its amplitude is given by 1 over square root of n. This is the initial starting point. Having done that, we define a Grover rotation operator by Rg equal to Us UW. So UW acts first and then Us acts, and we had last time seen that when this operator acts on an arbitrary state, it has the effect of rotating that state by an angle which is the twice of the initial angle that it makes with the marked state. So if you start with a particular value, every rotation by Grover operator Us UW will make it closer by 2 theta if initial angle between the marked state and the uniform distribution was theta. Now that makes the arbitrary state come closer and closer to the marked state, but there is a problem, that is, we must a priori know how much or how many times I must apply this Grover operator, because once, since it's a rotation, once it has exceeded that marked place, then of course the distance between them will go on increasing. So this is what actually happens, and so therefore this is what we did. We gave the geometrical interpretation, and today I will give a slightly different interpretation of the Grover rotation, because while geometry is extremely attractive, but it is not, doesn't really take us very far in trying to prepare an algorithm. So let us look at what is this new interpretation that we have. So we again start with an arbitrary state psi, which I will expand in the computational basis. So computational basis I am writing as x, and let us suppose that this is Ax. So this is an arbitrary state, and we have seen that my standard state S is simply an equal linear combination of these computational bases. So this is standard and this is arbitrary. So that what we have here, supposing I take the scalar product of S with psi, then this is 1 over square root of n by normalization. This will be sum over x, Ax and Xx of course. So which is nothing but 1 over square root of n times sum over x Ax. Actually I should have written it like this, Xx prime, so that by this should be just a scalar product of x with x prime, so that this is delta Xx prime, and this is what I get. Now look at what is this. If you look at this, what you find that this is equal to, this Ax is the amplitude of x in the state psi. So I can write this as, if I define A bar is defined as 1 over n sum over x Ax, which is nothing but the mean amplitude then I can write this as S with psi as equal to square root of n times the mean amplitude A bar, where A bar is simply the arithmetic average of the amplitudes of psi in a computational basis. Now let us look at what does US acting on psi give me. Our definition of US was U 2 times SS minus identity, and this is acting on psi, which is sum over x AX x. So this is equal to 2 times, notice I have here the S with psi, because this is actually psi, and minus psi, of course. Now this we have just now seen is given by square root of n times A bar. So therefore this quantity is 2 times square root of n times A bar. This is this quantity, and of course I have got the vector S there minus psi. So what I can do is to write this as equal to sum over x 2 times A bar minus AX x. Now this is just the expression for psi, and I have expressed now S in terms of 1 over square root of n sum over x, so that this becomes an identity. So notice what is the interpretation of the application of US on an arbitrary state psi. So what has happened is this, that before application of US, my amplitude of x in my state psi was AX. Recall, my psi was sum over x AXX. So this was before US is applied, and we have just now said that US of psi has become sum over x 2 times the mean amplitude minus AX acting on x. Now suppose I measure the amplitude with respect to the mean, then my initial amplitude with respect to the mean was AX minus A bar, and since my final amplitude is 2 A bar minus AX, so if I compute it with respect to A bar, this is becoming A bar minus AX. So this gets inverted. Now this is a nice observation to make, that the amplitude with respect to the mean of an arbitrary state on application of US gets flipped or inverted. Now we will see the meaning or what happens as a result of this. Let me take as a specific example number of items to be equal to 8. We had seen that n is equal to 4 gives us with a single Grover rotation the marked state. Now let's suppose I have n is equal to 8. I don't actually care which one is the marked state, because the oracle knows it by calculation of the function fw of x. So therefore I will assume that the oracle knows it, and my analysis of it is going to backtrack with the knowledge that Oracle has, what actually has been happening. So let's look at that. Supposing n is equal to 8, and let us suppose w is equal to 4. This is the illustration. You could take w equal to anything else, because all the states have the same status, it won't make any difference to our calculation. So in S, each basis state has a strength 1 over square root of 8. This is the amplitude of each of the computational bases in the standard state. Now, what does UW do? This is not US, this is UW. Now, what we had seen is UW will invert the amplitude of W only. UW inverts the amplitude of W alone. So since my starting point has also been 1 over square root of 8, after application of UW, the amplitude of W becomes minus 1 over square root of 8. All others still remain 1 over square root of 8. So let us recalculate the mean. Now my mean then is, there are 8 items of 1 over 8, 7 of them still has 1 over square root of 8 as the amplitude. The marked state has minus 1 over square root of 8 as the amplitude. So this is equal to 6 by square root of 8, and that is nothing but 3 by 8 square root 2. So now I look at what does application of US give me. Now notice, we said that as a result of US, the new amplitude will become A bar minus AX. So let us look at what does it mean. Let us rewrite mean is equal to 3 by 8 root 2. The unmarked state, let us call it U, unmarked state, there are 7 of them. The amplitude is 1 over square root of 8. The marked state, which is, we have been calling it as W, is minus 1 over square root of 8, and that's how I got these means. So let us look at what is happening by means of that. So every unmarked state will have an amplitude 2 times A bar. The A bar I have already written down. So 2 times A bar is 3 by 4 square root of 2 minus 1 over square root of 8, which is 1 over 2 square root of 2, and that's equal to 1 by 4 square root of 2. The marked state, which is W, remember it had a sign difference, so therefore this will be 3 by 4 square root of 2 plus 1 by 2 square root of 2, which is nothing but 5 by 4 square root of 2. Compare these. On comparison of these two, you find that the marked state's amplitude has been amplified so that it is 5 times as much as the unmarked state amplitude, which means the corresponding probability density has become 25 times. Now this is what we are calling as the selective amplification, and look at the picture here. So initially I have this state S, it's not visible here, but there is a red color there, and that is my marked state, the fourth one. The application of UW will invert that, leave all others the same. When you apply US after that, all these become much smaller and this becomes amplified so that the amplitude is 5 times as much. So the probability becomes 25 times. Next question that we want to ask is, we have already pointed out that we must a priori know the number of iterations, because if you don't, then since every rotation is making it closer to the marked state by an angle 2 theta, there would be a time when you will actually exceed it. Of course, it could still lie closer to the marked state than the previous one on the other side, but very soon it is going to be different. So therefore, we must be in a position to control how many times I want to apply the Grover rotation. That's very easy to calculate. Look at the slide that gives you the structure. I will work it out on the table. The angle between S and W in our diagram that I showed you last time was pi by 2 minus theta. Pi by 2 minus theta because I had taken sine theta equal to 1 over square root of n. Now since each Grover rotation rotates it by an angle 2 theta, if you have m number of rotations, the angle of rotation is m times 2 theta. Now this m times 2 theta should be as close to pi by 2 minus theta as possible, and in the ideal case it should just be equal to pi by 2 minus theta, which we saw was possible in case of n is equal to 4. In case of n is equal to 4, if you recall, my theta was 30 degrees because sine of 1 over square root of 4. So if sine that was theta was 30 degrees, 2 theta is 60 degrees, and pi by 2 minus theta is also 60 degrees. So therefore m is equal to 1 was the only solution. Now if you solve this in general, then you notice m must be equal to, approximately equal to, but pi by 4 theta minus 1 over 2. Now since we have said theta is equal to sine theta equal to 1 over square root of n, for large n I can ignore this term and I can find that m is equal to pi square root of n by 4. This is the quadratic acceleration that I was talking to you. That is the number of iterations after which the standard state on which when I applied the Grover iteration will come as close to the marked state as possible with very large amplitude is of the order of square root of n. Now what I have done, which you can very easily do in your leisure time, I have taken a very large number, but typically a database search will have much more. So try to work this out. It's a very trivial program that you read. This n is equal to 4096. I have taken 4096 because it just happens to be the square of 64. So that initially my amplitudes are 1 by 64. What I have plotted here is variation of the amplitude that I have got of the marked state as a function of number of iterations. Now what is found here is that when the number of iteration is 49, you will find that if you take that formula that I gave you, it comes very close to 50. Then the amplitude of the marked state almost becomes equal to 1. And after that, however, the amplitude starts decreasing with respect to this 49, and then it will sort of complete cycles. So what we have done in this lecture is to look at an interpretation of the Grover rotation in terms of the fact that it inverts the amplitude about the mean, and we had seen that as a result of that, the amplitude of the marked state gets selectively amplified, and with a very large degree of probability, if the number of iterations is of the order of square root of n, I would get the standard state with which I started coming close to the marked state which I am looking for.